Great. Yeah, thanks for that intro. As Emily said, my name is Felipe Parodi, and I am going to be talking about using pose estimation to study unrestrained social interactions in the Rhesus macaque. And I'll spend the next 5 minutes talking a bit about quantifying social behavior in the macaque, what's been done so far, and what we're excited to do in the future. So to start, I want to introduce our main character, the Rhesus macaque. One of the most important model organisms in neuroscience and other fields. They're impressive for a variety of reasons. So one of the ways to gauge an animal's success is by using the criteria of population size and geographic distribution. And when we look at this in the Rhesus macaque, it turns out that this animal is just as successful as humans. And this is largely due to their social nature. And for social primates like humans and macaques, their success largely depends upon their ability to cooperate, compete, and emotionally bookkeep. That is, track and remember previous social interactions. And this is significant because social deficits in both humans and macaques is associated with chronic deleterious impacts on health and well-being, making their study a priority. And so how can we study social behavior in the Rhesus macaque? A tried and true method to employ techniques is to employ techniques such as focal animal sampling to manually inventory the behaviors of a single animal to construct what is called an ethogram, which is exciting and useful, but it comes with a number of issues. Conducting ethograms is time and labor intensive, and it's pretty vulnerable to experimenter bias. Now in the lab, on the other hand, studies in humans and macaques alike have been restricted to highly controlled settings, largely for practical reasons. These studies typically involve restraining a monkey, as we can see here, so that it can interact with a computer, often completing economic games. And what people have done is record from an electrode and associate neural signals with mathematically tractable variables modeled through game theory. And this research is exciting and valuable, but as Yale Niv recently put it, we tend to overestimate neural data while largely underestimating behavior. You see, measuring behavior in highly controlled lab settings is a bit inorganic, and I think intuitively most of us feel this way. And so the big issue is that we simply don't know the extent to which the specific neural processes identified through these approaches contribute to real-world social interactions. And so fortunately, recent advances in deep learning-based pose estimation, like DeepLabCut, have given us this rich opportunity to measure animals and their naturalistic social interactions. So to train deep neural networks, a big challenge is simply not having enough data. However, we can now leverage available macaque data sets, such as OpenMonkeyPose and MacaquePose, to train a network to track Rhesus macaques moving through space and time. Okay, so how exactly do we track poses? Well, a typical framework tends to involve recording some video, extracting frames to label features of interest, and training a network to detect these features. We then apply a connected skeleton and use this model to analyze new and diverse interactions. And down the road, we can conduct further analyses to look at three-dimensional pose estimation. On the right here, we have a picture of some recordings I was working with using DeepLabCut. We have a frame of one macaque grooming another. The colored dots represent our features of interest, which include left ankle, left knee, hip, among other joints. And we have the XY plot of the feature trajectories. Now, this talk was really just intended to give you some ideas of the projects I'll be working on. However, they're not exactly without their challenges. And so some challenges we face include 3D pose estimation with a nice asterisk next to it, as OpenMonkey Studio, published last month, has managed a way around this with an interesting but complex setup. Tracking in real time with another asterisk next to it, as our third presentation today, I believe we'll talk more about this. And proper segmentation is yet another issue, which is simply the partitioning of an image into segments used to locate specific objects or boundaries. And finally, the embedding problem, or the ability for a computer to make sense of a given pose. See, poses tend to reflect context-dependent strategies, and with an animal that has as many degrees of freedom as a macaque, this isn't an easy task. So finally, some long-term questions we hope to pursue include taking neural recordings during naturalistic interactions between a pair of monkeys, like in the grooming image we just saw, or in group settings. And this would obviously be exciting to further characterize the neural processes underlying the macaque's social hierarchy, for example. Another approach is to the fully automated quantification of social interactions. Now, we envision, or rather idealize, a high throughput pipeline which would be fed recordings of macaques interacting and would pop out an objective, accurate ethogram. And there are a couple of packages out there that do this. And finally, characterizing social brain circuits, really making sense of what processes and agents drive social behavior and what exactly happens in disorders where social impairment is common, such as autism and schizophrenia, which would be exciting. And so with that, thanks for listening. I'd like to thank the K-Lab, the Platt Labs, and all of the Neuromatch organizers, including Emily and Gowri.
Thank you. Don't usually get thanked on the slides. That's very nice. All right, so while we wait for some questions for the audience to come in, I had a few questions. So first was relating to the pair interactions. How do you track two entities and make sure that they are treated as like separate and their identities are kept with them throughout the tracking, even if they are like, say, passing in front of each other or over each other if you're doing like 3D tracking?
Yeah, so you're referring to like pose tracking two separate individuals?
Yes. Yeah.
Yeah, and so DeepLabCut actually came out with like a multi-animal, like DeepLabCut multi-animal scenario. And so there, what you could do is you could identify two different individuals and apply a skeleton for each, and it would use like bottom-up image processing to like once it finds the left ankle or the left like a specific joint of one individual, it will connect the rest of the skeleton. But that's one of the issues I encountered. I mean, like these past 2 months, I've been working on it, right? The left ankle of one macaque tends to get confused for the right hand of another. Yeah.
Thank you. All right, we have questions coming in. The first one that I saw was from Melissa Franch from the Jorkboy Lab, who has two questions. First is, how many cameras are you using? And second is, have you attempted to quantify behavior that defines social hierarchy between pair-housed animals in captivity? And if so, do any behaviors stand out?
Yeah, so the camera question, the answer is like right now I've simply been working with 6 cameras. The goal is to get my hands on a larger number of cameras, ideally like in the 30s, about 32 cameras, and these would be 32 machine vision cameras. And so like OpenMonkey Studio, the Hayden and Zimmerman labs, and at U Minnesota, they're working with about 62 cameras, I think, with an entire setup to triangulate their 2D poses. The second question, have I attempted to quantify behavior that defines social hierarchy? No, and that's actually one of the things I'd like to do moving forward, right? And so I'm particularly interested in social cognition and decision making, and I don't exactly know how I would go about that just yet, but I appreciate the question.
Great, thank you. And then we have another one from Jesse Fu, who asks, what is the maximum number of animals that can be tracked with the current tools with good resolution?
Yeah. That's a good question that I don't think I know the answer to. So like any animal in general, I know there's a lot of work. So like humans, like pose estimation in humans is phenomenal, right? We can track entire groups of humans with just about no problem. And I think mice, which I believe Gary will talk about later, like mice work is also, we can track, I don't know, up to like 3, maybe 4, or even more at a time. And as for macaques, it's right now it's only really at like 1 to 2 macaques, and you saw like the 2 data sets that just came out that were on a slide earlier. I mean, they just came out. One of them is still a preprint; it hasn't been published yet.
Very cool. And Zerna, do you want to ask your question? You can just unmute.
Yeah, sure. Hi. So my question is, how large is the area that you're covering right now with your 6 cameras, and and why do you think that the 32 cameras would be necessary?
Yeah, okay. Good question. So the area right now, I'd say it's about, so it's a hexagon, and I'd say it's about 10 feet across. think like panel to panel. And height, it's about 10 feet tall as well. Now, so like why did I throw out the number 32 cameras? So like I met with Jan Zimmerman a while ago, and that's kind of the number he gave me to start gauging like when we're working with a specific number of cameras to do 3D pose tracking. This is kind of like the number of cameras that will help you out, right? With a specific model organism that has as many degrees of freedom as the Rhesus macaque, right? Things are a bit different when you're looking at the side view of a horse, for example, or really just a primate face. Yeah. These are a lot of questions.
Yeah, I have another one, which is about tracking. And this is also a question I'm going to ask to Gowri as well when we get to his talk, is tracking in disordered contexts. So making sure that tracking that works for normal, healthy movement is also going to work for tracking like a Parkinson's model or an MS model or an ALS model.
Oh, I'm sorry. I don't think I caught the question exactly.
Oh, sorry. So the question is I kind of would envision that there would be some challenges with making sure that you're comparing apples to apples. I could envision a scenario where you need to actually label frames from a motor disorder model and the controls separately, and that then you might not be tracking things with the same fidelity.
Yeah.
I mean, do you get that impression from, I don't know the behind the scenes about the algorithms, but do you get that impression that you would need to do that, and would that lead to some kind of differences in the labels that you would get out from those two data sets?
No, that's a great question. And I know, like, at least I know, like, in humans, to look at like impairments in gait and any other specific like skeletal muscle disorders, right? They do include like a very diverse data set that includes that would include the specific, like an impaired gait, for example. And I imagine if we're looking at like a Rhesus macaque, I don't know what a specific altered behavior would look like. But yeah, I imagine we should include it in the data set. And if anyone's opinion differs, I'd love to hear that.
Maybe Gowri can share after his talk. Okay, well, that has led us pretty much right up to the 15. So thank you everybody for all of those questions. If you have any more, you can post them to the chat or to the Q&A, and Felipe can answer them there. Thank you again, Felipe, for that great talk and lots of great answers.